All right, today we're jumping into one of the biggest puzzles in all of science. Seriously, it's a cosmic mystery that has some of the smartest people on the planet scratching their heads, and we're going to look at some new research that might finally be cracking the case.
So here's the problem in a nutshell. When we try to measure how fast the universe is expanding, our two best methods give us two different answers. And we're not talking about a tiny rounding error here. This is a major disagreement about how the cosmos actually works. Both of these answers can't be right.
And this isn't just some academic question. Getting a single, solid answer is absolutely crucial. This one number underpins, well, pretty much everything we think we know about the history, the age, and even the ultimate fate of our universe. So let's dig into where this disagreement actually comes from.
Okay, so on one side, we look way back in time at the early universe, basically the faint afterglow from the Big Bang. That data tells us the universe is expanding at about 67.4 kilometers per second per megaparsec. Now don't worry about megaparsec, it's just a gigantic cosmic yardstick. It basically means for every 3.26 million light years you look farther out, a galaxy is moving away 67.4 kilometers a second faster. But when we measure stuff that's closer to us, in the local universe, using things like exploding stars, we get a different, faster number, 73. This whole disagreement has a name, the Hubble tension.
And believe me, this isn't just some small debate for scientists. A contradiction this big could mean our standard model of cosmology, our best rulebook for the universe, has a huge hole in it. It's a really big deal. So just to be clear, we have these two completely trusted ways of measuring the cosmos, and they just don't agree. One method looks at the ancient light from the Big Bang, called the cosmic microwave background. The other looks at nearby exploding stars, or supernovae. And the most important part? The gap between the results is what we call statistically significant. That's science speak for, this is probably not a fluke or a measurement mistake. It's like the universe is telling us two different things at once.
And scientists are totally aware of how big a deal this is. I mean, look at this quote from the very research paper we're digging into today. They call it one of the most challenging problems in modern cosmology. They're not messing around.
But what if there was a third way to measure things? A completely new tool that could act as a tiebreaker? Well, that's exactly where this new research comes in, and it uses some of the most bizarre signals in the entire universe.
Let me introduce you to fast radio bursts, or FRBs. These things are wild. They are these unbelievably powerful flashes of radio waves that last for just a millisecond, a thousandth of a second. We know they're coming from galaxies billions of light years away, but the craziest part is we still don't really know what's making them. They're true cosmic ghosts, and they might just hold the key to this whole mystery. So, how on earth can we use a mysterious flash of light to measure the universe? The secret is in something called the dispersion measure. You see, as an FRB signal zips across the cosmos, it travels through all this super thin gas that has free electrons floating around. Think of these electrons like a kind of cosmic fog. They slow the radio waves down just a tiny, tiny bit. By measuring how much that signal gets smeared out, we can basically count up all the electrons between us and that burst.
And this is where things get really clever. Scientists realized they can use that electron count as a brand new kind of cosmic ruler. But to do that, they have to be super careful about decoding the signal.
You see, the total amount of fog the signal passes through comes from three different places. First, you have to subtract all the fog from right here in our own Milky Way galaxy. Then you have to estimate and subtract the fog from the FRB's home galaxy billions of light years away. Once you've peeled those two layers away, what you're left with is the signal that traveled through the enormous, almost empty space between galaxies, the intergalactic medium.
And that part, the intergalactic medium, is everything. Here's the core idea. The amount of that cosmic fog a signal has to push through is directly tied to how much space is stretched out. Think about it. If the universe expanded really fast, all those electrons would be spread out more thinly. If it expanded slower, the fog would be denser. So by measuring the density of that fog, scientists can actually calculate the universe's expansion rate. It's brilliant.
So the researchers took this idea and applied it to a list of 97 fast radio bursts, where we also know how far away they are. Every single one of those little millisecond-long bursts gives them one data point on their chart. The real challenge is taking all those scattered points and pulling out one single, precise number for the expansion of the universe.
So, after all that incredibly clever decoding, what do they find? What's the new speed limit for our universe? Well, to be really thorough, the researchers didn't just use one method. They ran their data through a few different statistical models, and as you can see, that gave them a range of different answers.
Some came in low, around 53, others went as high as almost 80. But one particular method, the one designed to find the most probable value, really stood out.
And here it is, the big reveal. Their most precise, most statistically sound result for the expansion of the universe landed at 70.10 kilometers per second per megaparsec. So the big question is, where does this new number fit in? Remember our two dueling values, 67.4 from the early universe and 73 from the local universe? Well, this new measurement of 70.1 lands almost perfectly in the middle of them. It doesn't really side with either one. Instead, it might just be the bridge that connects them.
Now, this is a seriously promising result, but you have to remember it's based on only 97 of these FRBs. The real power of this new technique is really just getting started.
Just take a look at this. This is a simulation from the paper that shows what the data could look like once we have a sample of 500 FRBs. And that's not science fiction. Our radio telescopes are finding more and more of these things all the time. The catalog is growing fast.
And this is exactly why more data is so critical. With the current sample of 97 FRBs, the measurement has an uncertainty of about 6%. But the study shows that with 500 or more, that uncertainty could drop all the way down to just 1.5%. That would make this method just as precise as our best current techniques.
So the big takeaway here is pretty simple. We are right on the edge of a data explosion. As we start detecting thousands of these FRBs, this method could finally give us the definitive answer we've all been searching for and finally resolve the Hubble tension for good.
And that leaves us with this one last incredible thought. For decades, our understanding of the universe has been split right down the middle by this cosmic contradiction. And now, it looks like the solution might come from these mysterious, fleeting signals that blink in and out of existence in a thousandth of a second. It's just a beautiful reminder that sometimes the universe's biggest secrets are hidden in its briefest moments.